Okay, so this will be recorded. So when you are working on the questions for the in-lab, you can always come back. I'll try to post it as soon as possible after the lecture. I'm going to post it, so you can come back and watch the lecture to answer some of the questions in the in-lab. And not everyone was in the lecture on Wednesday, but most of you were. And I talked about this a little bit. Not sure if you still remember that for the in-lab. It's a bit small here. I didn't bring my mouse, but so what's happening for the interrupt? Okay, like what I said in the lecture. So we used that timer 1 interrupt to play the note, right? However, every time it triggers the interrupt or turn on the flag, it comes to the ISR, which is at the bottom. You can open it up on your desktop laptop. The same code is published on the website. It takes 4.1 milliseconds, right? Like what we said in the class. So every single node has a different frequency. How do we control that? Some of them are, we expect, 3.1 milliseconds probably, but interrupt is going to be triggered every 4.1 milliseconds. You get into the interrupt service routine, it do the timer 1 right, okay? It toggles the pin, so you can see, seems like it's toggling that speaker pin every 4.1 milliseconds. It's gonna be the same note. So why it works? That's a key point that I introduced on Wednesday. Oh no, I'm sorry, Monday. But I don't expect everyone to remember that. But could you still try to recall what we said on Monday? How do we control the frequency of the toggling? Because every time it gets into the interrupt routine, how long it takes? How did we calculate it? Remember? It's a 2 to the 16th counts, right? And it's counting at 16 megahertz. Remember? And we used these two numbers to find out. It runs through all the counts and turn on the flag. The whole process takes 4.1 something milliseconds, remember? So it takes 4.1 milliseconds to overflow, right? So we didn't give an initial value to the timer, which means it's gonna get into the interrupt routine, service routine, every 4.1 milliseconds, then toggle the speaker pin. So which means it comes into the interrupt every 4.1 milliseconds, toggle it, and then take another 4.1 milliseconds, toggle it again. So it's gonna be the same frequency all the time. However, it's not the case because we have this timer 1 as well. So the timer 1 right is being used here, just the same timer. So the interrupt and the timer here to play the note is the same timer. So the time we immediately get into the interrupt, and the timer will be rewritten immediately. So it's giving the timer 1 an initial value here. So what that means is it's going to shorten the duration, makes the timer to overflow. So you can keep writing a new value. You change the note, you detect a new note in the list. You put a new duration here, okay? So it's gonna change the time or the duration to interrupt the next time. All right. So every time it's changing because of the timer 1 right. So you're putting a new value into it. That's how you can change the different notes in the list. Okay, so that's how we play it. Now let's come back to this list of questions over here. The first one is to ask you look at the specs of the speaker. Okay, it's rather labeled over here. I'm going to post the video so you can see all these labels, right? So depending on different frequency, it has a different intensity or amplitude for the speaker. Okay, so for certain frequencies, the maximum volume will be just like 80 dB or something. Oh, sorry, this is 80 dB. So you look at diagram like this from the website and find out the answers for these questions, the first and second questions. Not a problem. And starting from the third one, we have to refer back to the schematic. So it could be a little bit confusing. So on the, remember you put the jumpers on the pins on the PCB board, right? So if you come back to the schematic, you'll figure out where they are and what that means. So there's the audio amplifier. Because the volume from the microcontroller is a low power, low volume. So you have to amplify it using an audio amplifier in order to drive that speaker, which is a high load. It's a heavy load. So if you look at the connections, so in the PCB schematic, if you haven't done that yet, so it's good to know here. For pre, is it pre? I think that means like pre-amplification or something. So he labeled the pre here. So pre. If they have the same name of the two nodes, which means they're actually electrically connected, even though they didn't draw a line to connect these 2 points, but actually they are on the physical layout of the PCB board. They are electrically connected. So it's the same name, means they are connected. So where it's got disconnected is over here. So that's 2 pins. It's gonna print 2 through holes on the PCB and without any connection in the middle. You see there's no connection, right? There's no connection over here. However, this one and this one, they are connected. Okay, the 2 pre's are connected, but 1 and 2 are not connected. So that's a place you put a little jumper. Remember the little jumper header? You place a jumper on the top, so you short the 2 pins. So if you put a jumper there, you are connecting the output of the low-pass filter, which is this guy. We are not designing the filter, so don't worry about that. It's just the output's being filtered out. So low signal will pass. Low pass. Yes, low signal will pass. Low frequency signal will pass, but high frequency will be filtered out. So if you want to use that low pass filter, you put a jumper here. The low pass filter will be directly shorted to the amplifier. Okay, and you need an input for the low pass filters. The low pass filter is not a signal generator. It filters high frequency signals. So if you look at here, the filter has a jumper wire as well. If you do not have the long cable, the female to female cable, connect from like one of the pins, we use RB5, right? Remember? We use RB5 to output signal to the speaker. If you do not connect RB5 to, for example, here, okay? Even though you have this one shorted, you are not getting any signal sent to the speaker because the speaker is connected to the audio amplifier. You know what I mean? If you understand the schematic, you know what's going on. Doesn't like, hey, you put a jumper here, you don't know where the signal goes, right? So now, let's say, if I do not want to use a low-pass filter, which is this guy, LPF, right? LPF, low-pass filter. If I just don't want to use it at all, which is what we did in lab4 actually. We didn't use a low-pass filter. So we just want to directly output the signal from our RB5 to the audio amplifier. So audio amplifier is required. Low-pass filter is probably not. It's not a hard requirement. If you don't filter out noises, you are still getting pulses from your microcontroller, just a square wave, like the timer controls frequency of the note, right? It's okay. It's just like 3.3 volts square wave. You can still directly connect that output to the audio amplifier. It's going to amplify it. Okay? It's going to buffering the signal and giving more power to it. So what you can do is, I'll let you guys tell me. If I do not want to use LPF, I can see there's the label here is probably, I don't know if this is still a current label for the new PCB. Anyway, doesn't matter. So you know that this pin, the other side of the header is connected to RC2. Okay, we're not using RC2. We're using RB5. Keep in mind, RB5 is the output. So RB5 is outputting the song signal, right? And we want to directly use the audio amplifier, connect to the input audio amplifier. We want to hear from the speaker. So where should we connect the jumper cable to? So the jumper cable, one side from RB5, right? The other side should be where? Just look at here. Should be where? where should I connect it to? That's actually a good question. By looking at here, I couldn't really tell. Let me see. So this line on the PCB board is what? I can tell now, okay, because I figured out. So these two connections is just what? Let me draw on the paper. Always think about the PCB, okay? Always think about the PCB. Remember, there's two connectors, right? And here's pre, whatever. Here's another pre, and that's the audio amplifier. Okay? So these two lines on the PCB, it's just a trace on the PCB printed on the board. So what is this one? This is a pin, right? It's the header pin. This is the header pin. Another header pin. Remember, you put a jumper here to make the connections. But for example, we don't put the jumper on the top. So what's happening is you have this header pin available, right? And you got a female cable here, connect to RB5. So we directly put this cable, connect to this male header, right? So what's happening is the RB5 signal will directly be sent through this female header to this male header pin and directly get into the audio amplifier. That's how that works. You don't need a jumper here. If you have a jumper, there's no place to plug in that female header, the female jumper cable. Does that make sense? So in lab 3, actually, that's what we did, but probably you didn't know why. So now here's why. You got the RB5, you know, there are male header pins of the microcontroller, right? You plug in, use the cable, the two female cable, connect, and the other way, the other side of the cable, which is here, you plug into I think it's amp. Is that amp in or something? Amp in on the board. You can look at the silk screen, the print. So the amp in, so the amplifier input. So the low pass filter is not engaged. Does that make sense? Okay, so you know what you did, okay? And now let's come back here. T1 con. So use a T1 control register to do the following tasks, like enable timer 1 and run at this frequency and do a 1-to-1 prescaler. So if you look at this guy, what are the bits controlling these functionalities? So see, look at this one. Okay, this is T1 con. Okay, T1 con, TX con, but it's T1 con. T1 con, and look at this. So that's the frequency you want to use. It's 64 megahertz divided by 4, which is giving you 16 megahertz. So there's a original or main clock where we never used actually. It's 64 megahertz. So if you pick up this 2 bits and give 0, 0 to it, so it's giving you 64 divided by 4, which is giving you like 16 megahertz, the frequency we have been using for the main clock of the CPU, right? So what about prescaler? You can see, hey, this is a prescaler, and I want to pick up 1-to-1 prescaler. Just choose the bits you want or you need, all right? And enable it. I want to turn it on, right? On bit. So we see what kind of bit will turn it on, which is actually over here. So the TMR1 on. Okay? That's what that means. UART, you just get into the UART function where you can see there are 2 UART functions are being called. One is the UART ready, another one is UART read. Very simple question. And the 2 calls on timer 1 set interrupt handler. So go to let me see which one I want to pick up. Let's try this. Oh no. So where that interrupt handler has been called was called. So first is in the main.c file. You'll see it's being called here first. All right, and then if you go to the interrupt manager, you'll see that timer 1, I think. Timer 1, yeah. timer 1 initialization, right? So here it's being called the second time. Right? So another one, what are you are looking for that function, the first word. The daughter function of interrupt manager. The daughter function of interrupt manager. So let's go to interrupt manager. How do we do that? Remember, I talked about that on Monday. Control click, right? So that's the interrupt manager function. You'll see, hey, this is a daughter function, okay? And then I control click, you'll find out I got another, it's called granddaughter function, okay? What does the daughter function do? The daughter function, let's take a look at the daughter function. Here's the daughter function. What does it do? Clear it. So why that is important? Clears the flag. Because that's the interrupt service routine. Every time the interrupt flag is on, it triggers or it calls that interrupt routine, service routine, okay? The flag is on, like what I said. The flag is on, right? You have to clear it. You have to clear it. So if you go back to the main C file, it gets into this at the bottom. Here is your interrupt service routine. Every 4.1 milliseconds gets into here, the flag will be on. However, because this is being called, so it clears it by itself, even though you don't see it. You don't see that flag is being cleared over here. But it's being cleared because it's running on the back scene. You can see the TSR, the TMR ISR is cleaning that, is clearing that bit, that flag. So you can do it again, you can use it again, right? Because sometimes in lab 3 you see the code, you have to clear that flag above this timer 1 write. But however, we don't have it here. I had the same question when I look at it at the very beginning. I was like, hey, where's that flag getting cleared? There was a huge question mark in my mind. But eventually I find out, oh, it's being cleared in the daughter and granddaughter function. It's hiding somewhere. See? Click. It's here. Okay? The interrupt handler handles that, takes that my ISR, which is this guy, eventually will call this function, the interrupt function, and clear up that bit. Let's keep going. I just pick up the ones will potentially confuse you. Oh, another thing, important. Not just for the in-lab, but also for the lab, okay? Still cannot zoom in. Look at a little control unit here. So think about that. Is the interrupt being controlled here? I mean, if you start running, you part it up. You have the code, download it to your microcontroller. You part it up, right? It's gonna start calling that interrupt function every 4.1 milliseconds. It's auto control. It's gonna always do that because it's called interrupt. It's gonna interrupt whatever is running in your main code. It's gonna get into here every 4.1 milliseconds for the first time. The second time, the duration of the takes to get into this interrupt will change depending on the note frequency because you are doing this timer 1 write. Okay, so you need another layer of control. Keep in mind, this is super important, not just for here, also for the lab. It's super important. It goes back to the main code, right? You can do whatever you do here, do there, over there. And that's the opportunity for you to turn on off some of the flags. It's not a flag in the interrupt in the register. You define the variable to define that flag. And why it's important? Take a look at here, the code. I know it's small, but if you couldn't see, just getting closer probably. That's super important, just let you know. You have to put that whatever you are doing in the interrupt routine inside that if statement. So you can add another layer of control, you know what I mean? You don't want to always play the music. If you watch the demo video, it's not always being played. You only press it. You press the key or you press the button on the board, then you turn on the flag. Which flag? It's called play note. Play note, it's just a variable. It's just a byte, okay? You put a true, put a false, doesn't matter. So you press it, in your main code, you give a true to it. So whenever it interrupts, because you cannot control the interrupt, like what I said, if you turn it on, it's gonna interrupt every 4.1 millisecond, right? It's gonna get into it no matter what you have done in the main C code or what the user has done with the board. So whenever the user do something or does something with the board, you want to use a flag to control it. You want to tell the interrupt, the next time you get into the interrupt, it sees that flag, which means the user has done something to the board. Very important, okay? Not just for this one, but also for the lab. Make sense? It has to be true in order to play it because someone pressed it. The interrupt is being called very frequently, only 4.1 milliseconds. All right? Another thing. So what you can do, and also the in-lab asks you to do, which is plug in a test pin. So test pin, I might be wrong. I couldn't remember the pin name, but it's just another output pin. I think in my step-by-step instruction on my website, I shows you how to set up two output pins. One is one drives the speaker, another one is the testing pin. You can see this is the testing pin. Why do we have the testing pin plugged into the interrupt? If you don't have it, you'll find out sometimes I don't even know the interrupt is being called. If the code is not working, I didn't hear anything, I don't even know what's going on. How could you tell the interrupt is being called or not? How could you tell? No way to tell. It's all running inside the chip. However, if you set up a testing pin, you know what this does? It's really interesting and very handy. So you put a high. Whenever it gets into interrupt, you give a high. And whenever it ends interrupt, at the bottom of the interrupt routine, you set a low. So what that means is it's going to give you a little pulse if it gets into it. If it ever gets into the interrupt routine, it set a pulse. And you can measure it using what? And you can visualize that using what in the lab? Oscilloscope. So you will be able to know if the code ever gets into the interrupt routine. Okay, you can test it. You put a high, you put a low at the bottom, you put a high at the top and low at the bottom. So it's going to create a pulse. So you can measure it, you probe it, you can see a pulse. That means the interrupt routine is being called. All the settings, the interrupt enable and whatever is correct. It's running. But if you couldn't hear anything, something wrong with the timer settings. Okay? You can even measure the width of the pulse, the duration of the pulse, to understand how long it takes to run the interrupt service routine. The top because it runs the code from top to bottom, that takes out every one single instruction from top to bottom, one by one, right? If you put this testing pin high on the top and testing pin low at the bottom, you will know exactly how long it takes to run everything in the interrupt service routine. Make sense? And you can even plug in this one somewhere else to measure how long it takes. It's just set high, set low, so you can measure it. So you know from here to here, like how long it takes to run it. So this covers several questions in the in-lab, if you understand how to do it. So there will be some hands-on measurement with the oscilloscope. And there's another thing you probably couldn't see it. Oh, this is a pulse, okay? The set testing pin high, testing pin low, so you can measure the duration. And there's another thing, it's called slew rate. Have you learned slew rate somewhere else? Slew rate? No? Let me draw it on the paper. So many things to learn. Okay? Because all the pulses, if you zoom out, it looks like a very sharp pulse, like infinite. However, it's not. If you zoom in, how to zoom in? There's a time scale, a knob on the oscilloscope. Turn clockwise, zoom in, okay? Zoom in here. So see this, it's a ramp. So slew rate, you take 10%. 10%, this is 10% the amplitude. Here's 90%. Okay, measure. Oh, that's so rise time. Sorry, it's not slew rate, it's a slew rate. Slew rate, not slew rate yet. So it's the rising time. What's the rising time? 10% to 90%. Okay, that's the time. So get a time first, and you get a amplitude change. So which is that's a v delta v over delta t. Okay. I think there's a percentage for the unit. Sometimes it's not asking for the percentage. Let's take a look at what this one asks. It doesn't matter, just the voltage. It's voltage over t. It's like a slope, telling you how fast this changes in terms of voltage. Okay. Let's see. Let me see this. Not too much. Another thing I will bring up a little bit really quick, and the lab. So that's a template. Template. I think that's a template. Is it? Yeah, it is. This could be trickier and more difficult. I think I don't want to overwhelm you today. I don't know if any of you can reach to the lab today. Otherwise, I think I will cover it on Friday during the lecture. Okay, don't want to overwhelm you guys. So you can do a demo. You can start working in lab one. In lab one, answer the questions, do whatever you have to do. And this will be uploaded to my website in probably 10-15 minutes. Okay.